Hello there, and welcome to Simple Science for Sleep. Close your eyes for a moment and picture this. Right now, beneath your feet, there's a world larger than all the land you've ever walked on. A world that covers most of our planet. A world we've barely seen. The ocean holds mysteries we're only beginning to understand, and tonight, we're going to drift into some of its most incredible secrets together. Tonight, we're heading somewhere special. We're going beneath the waves, into the deep blue, to discover things that will change how you see the ocean forever. This is a place for calm curiosity and rest. A place where wonder and peace meet. So settle in. Get comfortable. Let your body sink into wherever you're resting, because we're about to begin a gentle journey through the most incredible ocean facts you've ever heard. The ocean is Earth's largest mystery. It covers over 70% of our planet's surface. That means if you looked at Earth from space, you'd see much more blue than green or brown. The ocean is vast beyond imagining. It's deeper than mountains are tall. It holds more life than all the land combined. And here's something that might surprise you. We know less about the deep ocean than we know about the surface of the moon. Think about that for a moment. We've sent robots to Mars. We've photographed distant galaxies. But the deepest parts of our own ocean remain almost completely unexplored. There are creatures down there we've never seen, landscapes we've never mapped, sounds we've never heard. The ocean keeps its secrets well. But tonight, we're going to explore some of what we do know. And what we know is already amazing enough to fill you with wonder. Before we dive deeper, I want to say something. If this brings you calm, if you enjoy these quiet journeys through science, I'd love for you to like this video and subscribe to the channel. You'll be joining a community of fellow science lovers who find peace in learning about our incredible world. And I'm curious, where are you listening from right now? What time is it there? Drop a comment and let me know. I love knowing where in the world these facts are traveling. Now, let's return to the ocean. The ocean is always moving. Even when the surface looks calm, currents flow beneath. Water circulates. Life drifts and swims and glows in the darkness. The ocean is never still, never silent, never empty. It's a living, breathing part of Earth. And actually, that word breathing is more accurate than you might think. Because here's where our journey really begins. The ocean doesn't just look like it breathes. It actually does breathe. For us. For every person on Earth. Every animal on land. The ocean is breathing right now, creating the very air that fills your lungs. And that's where we'll start to understand just how connected we are to this vast blue world. Every other breath you take comes from the ocean. Let that sink in for a moment. Breathe in, breathe out. One of those breaths was made possible by the ocean, not by trees in a forest, not by plants in a garden, by the ocean itself. How is this possible? The answer drifts in the water, invisible to your eyes, but working every single day to keep you alive. We're talking about phytoplankton. Phytoplankton. The name sounds complicated, but what they are is beautifully simple. They're tiny plants, so tiny you can't see them with your eyes. They float near the surface of the ocean, drifting with the currents, catching sunlight. And just like the trees outside your window, just like the grass in a park, these microscopic plants do something magical. They take in carbon dioxide and release oxygen. They breathe out what we breathe in. But here's what makes them so important. There are so many of them, an unimaginable number. If you filled a cup with ocean water, that single cup would hold millions of these tiny plants. Millions in one cup. Now imagine the entire ocean, all that water, all those waves. Every drop contains these invisible oxygen makers, working quietly, endlessly, keeping the air breathable for every creature on land. Scientists estimate that phytoplankton produce between 50 and 80% of the oxygen in Earth's atmosphere. That means most of the oxygen you've breathed in your entire life came from the ocean. Not from rainforests, though they help too. From these drifting microscopic plants that most people never even think about. Take a breath right now, a deep one. Feel your lungs fill. That breath was a gift from the ocean, from creatures so small you could fit thousands of them on the head of a pin. These tiny plants form the foundation of ocean life. Small fish eat them, bigger fish eat those fish. Whales filter them by the millions. Everything in the ocean depends on phytoplankton, either directly or indirectly. They're the beginning of almost every ocean food chain. But they do more than feed ocean creatures. They feed us too, not by eating them, though some cultures do, but by giving us the air we need, by regulating the climate, by absorbing carbon dioxide that would otherwise warm our planet too quickly. The ocean, through these tiny drifting plants, keeps Earth livable. It's been doing this for billions of years. Long before humans existed, long before any creature walked on land, the ocean was already breathing, already creating oxygen, already making life possible. And it's still doing it right now. While you rest, while you drift towards sleep, the ocean continues its ancient work. Phytoplankton near the surface catch the morning sun on one side of the world. On the other side, where it's night, they rest, ready to begin again at dawn. This happens every day, every single day. Waves roll, currents flow, and these invisible plants turn sunlight into the breath of life. Think about the air in your room right now. Some of those oxygen molecules were created by phytoplankton in the Pacific Ocean. Some came from the Atlantic, some from the Indian Ocean. The air you breathe is a gift that has traveled across the world, carried by wind, delivered to your lungs. You're connected to the ocean in this intimate way, even if you've never seen it, even if you live far inland, surrounded by mountains or plains or forests. The ocean's breath becomes your breath. Its life supports your life. This connection runs deeper than you might imagine. Because the ocean doesn't just give us air to breathe, it gives us life in other ways too. Ways that are even more surprising. Ways that are hidden beneath the surface, out of sight, working in darkness and silence. The ocean is full of invisible wonders. Rivers that flow underwater, lakes that exist beneath the waves, waterfalls that dwarf anything on land. These things seem impossible. Water flowing through water, but they're real, and they're stranger and more beautiful than you might expect. Let's sink a little deeper now, down past where the phytoplankton drift, down to where the water grows darker and colder, down to where the ocean reveals one of its most surprising secrets, down to where rivers flow in the deep. Imagine standing on a riverbank. You watch the water flow past, moving in one direction, cutting through the landscape. Now imagine that river is underwater, not flowing on top of the ocean, but through it. A river of water flowing through more water. It sounds impossible, but it's real. These underwater rivers exist because not all water is the same. Some water is saltier than other water. Some is colder. And when water has different salt levels or temperatures, it has different weight. Heavier water sinks below lighter water. And when there's enough heavy water flowing in the same direction, it forms a current. A river. An actual river with banks and a channel. Except both the river and the banks are made of water. The most famous underwater river flows beneath the Black Sea. Scientists discovered it using special equipment that can measure water density. What they found amazed them. A channel carved into the seafloor. Water flowing through that channel like a river flows through a valley. This underwater river is so defined that if you could somehow stand on its bottom and survive the pressure, you could actually boat on it. The river moves slowly through the darkness. It carries sediment and nutrients. Fish swim across it like birds flying over a land river. The water above flows in different directions, pulled by winds and tides. But this deep river follows its own path, carved over thousands of years. And it's not alone. Scientists keep finding more of these hidden currents, rivers flowing along ocean floors around the world. Some are cold and dense, sinking from polar regions. Others are warm and salty, flowing from tropical seas. They move through the deep ocean like a hidden circulatory system, distributing heat and nutrients across vast distances. But underwater rivers aren't the strangest thing flowing in the ocean. There are waterfalls too, underwater waterfalls, and they're enormous. The largest waterfall on Earth isn't on land. It's underwater, between Iceland and Greenland. It's called the Denmark Strait Cataract. Cold water from the Nordic seas meets warmer water from the Atlantic. The cold water is heavier, so it sinks. It plunges down in a massive underwater waterfall. How big is it? This waterfall drops more than 2 miles. That's over 3 times the height of the world's tallest building. It carries more than 2,000 times the water that flows over Niagara Falls. But you'd never know it's there by looking at the surface. The ocean above looks calm. Beneath, water crashes down in an endless, silent cascade. Picture this waterfall in your mind. Total darkness, crushing pressure, water falling through water in slow motion, creating currents that spread across the ocean floor. No one has ever seen it with their own eyes. No one could survive the depth and cold. But we know it's there, measured by instruments, confirmed by science. These underwater waterfalls happen wherever cold water meets warm water at an edge or slope. They're constantly flowing, constantly falling, moving water through the ocean's layers like blood through veins. And here's something even stranger. The ocean floor has lakes too. Not lakes on the bottom that you could see if you could drain the ocean, but actual lakes of different water sitting on the seafloor with shores and surfaces. Lakes within the ocean. These aren't rivers or waterfalls. They're pools. Still water within moving water. And they're so different from the surrounding ocean that fish can't swim through them. The boundary between the lake and the ocean is as real as the surface between air and water. What creates these impossible lakes? What lives at their strange shores? The answers reveal just how alien the deep ocean can be, even though it's part of our own planet. These underwater lakes are called brine pools. They form when salt deposits on the ocean floor dissolve into the water above them. This creates water that's much saltier than regular seawater. And because it's saltier, it's heavier. It sinks and stays down, forming a pool. The brine is so dense that it doesn't mix with the ocean water above it. Instead, it creates a distinct boundary, a surface. You could actually see where the lake begins if you were there. The transition is that sharp. Above the surface, fish swim through normal seawater. Below it, there's brine so salty that nothing can live in it. It's like a desert in the middle of the ocean. A dead zone surrounded by life. These pools can be small, just a few feet across, or they can stretch for miles. Some are round like ponds. Others follow the contours of the seafloor like rivers that stopped flowing. And they all share one thing: they're deadly. When a fish accidentally swims into a brine pool, it dies almost instantly. The salt is toxic at such high concentrations. The fish's body can't handle it. So these underwater lakes are surrounded by the bodies of creatures that wandered too close. It's an eerie sight, a pile of dead fish and crabs at the shore of an underwater lake, perfectly preserved by the salty water. But life finds a way even here. At the edges of these brine pools, where the super salty water meets normal seawater, special bacteria thrive. They've adapted to live in this transition zone. They feed on the chemicals in the brine, and other creatures feed on these bacteria. So even though the brine pool itself is dead, its shores are full of life. Scientists study these pools because they're similar to what oceans on other planets might be like. If there's liquid water on Europa, one of Jupiter's moons, it might have brine pools like these. Studying Earth's brine pools helps us understand what alien oceans could contain. Some brine pools bubble with methane gas. The gas seeps up from beneath the ocean floor and gets trapped in the brine. These pools look like they're boiling, even though they're ice cold. Bubbles rise through the thick liquid and pop at the surface. It's a strange, otherworldly scene. Imagine diving down and seeing this. You're swimming through dark water. Your lights cut through the blackness. And then suddenly, there's a pool below you, a lake on the ocean floor with a distinct surface. You can see ripples on that surface. You can see the clear boundary between two types of water. It looks exactly like flying over a lake instead of swimming above one. These brine pools remind us that the ocean isn't uniform. It's not just one big mass of water. It has layers, boundaries, regions as different from each other as a desert is from a rainforest. And in these different regions, life adapts in remarkable ways. The deep ocean, where no sunlight ever reaches, should be empty. It should be barren, but it's not. It's full of life that survives without the sun, without light, without anything we once thought life needed. And that's where we're heading next. Into the permanent darkness, where life learned to exist in ways that changed everything we thought we knew. Sunlight only reaches about 600 feet down into the ocean. Below that, it gets dimmer and dimmer until there's no light at all. This zone of permanent darkness covers most of the ocean floor. It's vast, it's cold, and for most of Earth's history, scientists assumed it was mostly empty. They were wrong. The deep ocean is crowded with life. Strange life. Life that survives without photosynthesis, without plants, without the sun's energy that powers almost everything on the surface. How? The answer is chemosynthesis. Instead of using sunlight for energy, these creatures use chemicals. Deep sea vents crack open in the ocean floor, releasing hot water full of minerals. Bacteria gather around these vents and absorb the chemicals. They turn those chemicals into energy, the same way plants turn sunlight into energy. And then other creatures eat those bacteria, a whole food chain built on chemistry instead of light. The vents themselves are extraordinary. Water superheated by the Earth's core shoots up through cracks in the rock. The water is hot enough to melt lead, but the pressure is so intense that it doesn't boil. It just pours out in dark, mineral-rich plumes. Around these vents, life clusters in abundance. Giant tube worms grow as tall as a person. They have no mouth, no stomach, no way to eat. Instead, they have bacteria living inside their bodies. The bacteria process the chemicals from the vent. The tube worms absorb the nutrients the bacteria produce. It's a partnership. Neither could survive alone. There are blind white crabs scuttling across the rocks. Pale fish that have never seen light. Clusters of mussels covering every surface. All of them feeding on bacteria. All of them thriving in conditions that would kill most surface creatures instantly. This discovery changed everything. Before scientists found these deep-sea vents in the late 1970s, we thought all life on Earth ultimately depended on the sun. But here was proof that life could exist independently, that life could tap into Earth's internal heat instead of the sun's light. It meant life was more resilient than we imagined, more creative, more determined to exist wherever it possibly could. And it changed how we think about life on other planets. If life can survive in the pitch black, crushing depths of Earth's ocean, feeding on chemicals from volcanic vents, then maybe it can survive in the ice-covered oceans of distant moons. Maybe life doesn't need a sun at all. Maybe it just needs water and energy, in whatever form that energy comes. The deep ocean showed us that life is stubborn. It finds a way. It adapts to impossible conditions. It survives in places we never thought to look. But these creatures aren't just surviving. They're communicating. They're hunting. They're finding mates in total darkness. And they do it with their own light. The deep ocean doesn't stay completely dark. The creatures themselves light it up. Most animals in the deep sea can create light within their own bodies. They glow, they flash, they shine in the endless night. And this ability to make light is so common down there that it's almost stranger to find a creature that can't do it. The ocean, it turns out, knows how to light itself. Bioluminescence. It's the ability to create light from your own body. And in the deep ocean, it's everywhere. Scientists estimate that up to 90% of deep-sea creatures can produce their own light. Think about that. 9 out of every 10 animals down there glow. It's not rare. It's normal. It's expected. If you could swim through the deep ocean, you'd be surrounded by living lights in every direction. The light comes from a chemical reaction inside their bodies. Special cells contain chemicals that, when mixed together, produce light. It's similar to how a glow stick works. Break the stick, the chemicals mix, and it glows. But these creatures control it. They can turn their lights on and off, flash them in patterns, make them brighter or dimmer. They've mastered their own internal light show, and the effect is breathtaking. Imagine floating in complete darkness. Then a jellyfish drifts past, its bell pulsing with blue light. A fish swims by with rows of lights along its body like windows on a ship. Another creature blinks in the distance, then another and another. Soon you're surrounded by thousands of tiny lights, floating and flickering in the void. It's like swimming through space, like drifting among stars. Except these stars are alive. These stars are watching you. These stars have their own purposes, their own sense, their own silent conversations, happening in flashes of light. The colors vary. Most bioluminescence is blue or green because these colors travel farthest through water. Red light gets absorbed quickly in the ocean, so it's rare. But some creatures do produce red light, which gives them an advantage. Most deep-sea creatures can't see red, so a fish with a red light can hunt using a beam that's invisible to its prey. The patterns are just as varied. Some creatures glow steadily. Others flash rapidly. Some create waves of light that ripple across their bodies. There are fish that light up their entire bodies. Others that only glow from specific spots. Some have light organs around their eyes like headlights. Others have them on their bellies or tails or fins. This isn't random decoration. Every light serves a purpose. Every flash means something. In the deep ocean, where sound doesn't travel as well as it does closer to the surface, light becomes language. Light becomes survival. And the ocean pulses with these conversations every night. Creatures calling to each other, warning each other, hunting each other, all through silent bursts of living light. Scientists diving in submarines describe it as one of the most beautiful things they've ever seen. A light show no human created. A display more intricate than any fireworks. And it's happening right now, in the depths, unseen by almost everyone. The ocean makes its own light because it needs to. Because in the permanent darkness, light becomes precious. It becomes a tool, a weapon, a signal, a disguise. But why do they create this light? What purpose does all this glowing serve? The reasons are as clever and surprising as the lights themselves. Each flash, each glow, each pulse of bioluminescence is solving a problem. And understanding these reasons shows us just how intelligent and adapted these creatures really are. The first reason is the simplest: finding a mate. In the vast darkness of the deep ocean, creatures are spread far apart. You might swim for hours without seeing another of your species. So, when it's time to reproduce, you need a way to signal. You need to say, "Here I am. Many fish flash specific patterns that only their species recognizes. It's like a secret code. The male flashes a sequence. The female recognizes it and flashes back. They find each other through their lights, even across great distances. Without this ability, many deep-sea species would go extinct. They'd never be able to find each other in time. The second reason is hunting. Some predators use light like a fishing lure. The anglerfish is famous for this. It has a long spine growing from its head with a glowing tip. The light dangles in front of its mouth. Small fish see the light, think it's food, and swim closer. Then, the anglerfish strikes. Its jaw opens wide, and it swallows the prey whole. Other hunters use light differently. Some flash bright bursts to stun their prey. The sudden light blinds or confuses the victim for just a moment. That's all the predator needs. One moment of confusion and the hunt is over. The third reason is one of the cleverest: camouflage. This sounds backward. How does glowing help you hide? But it works perfectly. Many fish have light organs on their bellies. When they swim, there's faint light coming from above, from the distant surface. Predators below look up and see the silhouette of the fish against this dim light. But if the fish lights up its belly to match the light from above, its silhouette disappears. It becomes invisible from below. The predator sees right through it. This is called counter-illumination, and it's brilliant. The fish has to adjust the brightness constantly as it swims through different depths. Too bright and it stands out. Too dim and the silhouette shows. But when it's just right, the fish vanishes. The fourth reason is defense. Some creatures, when attacked, release a cloud of glowing chemicals. It's like a smoke bomb made of light. The predator gets confused or distracted, and while it's trying to figure out what just happened, the prey escapes into the darkness. Other creatures do something even more clever. They coat their attacker with glowing slime. The predator suddenly lights up like a beacon. Other, larger predators see this light and come to investigate. The attacker becomes the prey. It has to flee or become someone else's meal. And the fifth reason is communication. Deep-sea creatures flash patterns at each other that might mean warnings, threats, or information. We don't understand most of these signals yet, but we know they're happening. Conversations in light, taking place in the darkest parts of the ocean. All of this happens in silence. Light doesn't make sound, so the deep ocean is filled with glowing creatures having entire interactions without a single noise. But the ocean isn't actually silent. Not at all. We just can't hear it from the surface. Beneath the waves, sound travels far and carries weight. And some of the most beautiful sounds on Earth are happening underwater right now. If you could listen underwater, the ocean would surprise you. It's loud, it's busy, it's full of sounds we never hear from above the surface. Sound travels differently through water. It moves faster and farther than it does through air. A sound made underwater can travel for hundreds of miles before fading. This makes the ocean perfect for long-distance communication, and creatures have learned to use it. Shrimp click their claws so loudly that colonies of them create a crackling sound that can deafen sonar equipment. It sounds like bacon frying, but amplified across entire reefs. These clicks are constant, day and night, creating a background noise that fills shallow oceans. Ice groans as it shifts and cracks. In polar waters, the sound of icebergs breaking and grinding against each other echoes through the depths. It's a deep, rumbling sound. Sometimes it sounds like thunder, sometimes like a distant avalanche. It reminds you that ice, even though it seems still and solid, is always moving. Earthquakes rumble through the ocean floor, sending vibrations through the water that can be heard thousands of miles away. The Earth itself is noisy underwater. Volcanic vents hiss, tectonic plates grind. The planet makes sounds we never hear on land. But the most beautiful sounds in the ocean come from whales. Whale songs are exactly that. Songs. They're not random noises. They're structured, repeated, musical patterns. Humpback whales are famous for this. A male humpback will sing the same song for hours, sometimes for days. The song has verses and phrases. It repeats in a pattern. And here's what makes it incredible. All the humpback whales in one region sing the same song. They all know it. They all perform it. And the song changes over time. Slowly, over months and years, the whales modify it. They add new phrases. They drop old ones. They change the rhythm slightly. It evolves like human music evolves. And all the whales in that region learn the new version. They stay in sync. Scientists still don't fully understand how they coordinate this. These songs can last for 30 minutes or more. Then, the whale takes a breath and starts again. The same song, over and over. And other whales hundreds of miles away can hear it. The sound carries across entire oceans. Blue whales produce the loudest sound of any animal on Earth. Their calls can reach 180 decibels. That's louder than a jet engine. These calls travel thousands of miles through the deep ocean. A blue whale off the coast of California can be heard by another blue whale near Alaska. They're having conversations across distances we can barely imagine. Scientists believe these songs serve multiple purposes: finding mates, marking territory, staying in contact with family groups spread across vast distances, maybe even sharing information about food sources or dangers. We're only beginning to understand this underwater language. We know whales are communicating. We know their songs are complex and meaningful. But we don't know exactly what they're saying. We're listening to conversations we can't quite translate. And these singers, these creatures with voices that span oceans, are some of the most remarkable animals on Earth. The whales themselves are worth understanding, especially the largest of them all. The blue whale is the largest animal that has ever lived. Not just the largest alive today, the largest ever. Bigger than any dinosaur. Bigger than anything that has ever existed on this planet. An adult blue whale can grow to 100 feet long. That's longer than 3 school buses parked end to end. It can weigh 200 tons. That's as much as 30 elephants. Its heart alone is the size of a small car. A human could crawl through its largest blood vessels. When a blue whale surfaces to breathe, its blow, the spray of water and air from its blowhole, can shoot 30 feet into the air. That's as tall as a 3-story building. You can see it from miles away. But here's what's truly amazing. This massive creature the largest animal ever to exist, survives by eating some of the smallest creatures in the ocean. Krill, tiny shrimp-like animals, each one no bigger than your thumb. The whale feeds by gulping enormous amounts of water, sometimes swallowing 50 tons at once. Its throat expands like an accordion to hold all that water. Then it closes its mouth and pushes the water back out through baleen plates that hang from its upper jaw. These plates are made of keratin, the same material as your fingernails. They act as a filter, trapping the krill while the water escapes. A blue whale can eat up to 4 tons of krill per day during feeding season. 4 tons. That's 8,000 pounds of these tiny creatures, filtered from the ocean one gulp at a time. The whale's tongue weighs as much as an elephant. Its flippers are longer than most people are tall. Even its tail flukes, which propel this giant through the water, are wider than a bedroom. Despite its size, the blue whale is surprisingly graceful. It can dive to depths of 1,000 feet, holding its breath for 20 minutes or more. When it's down there, its heart rate slows, way down, sometimes to just 2 beats per minute. 2. Your heart beats 60 to 100 times per minute at rest. The blue whale's heart beats twice. This slow heartbeat conserves oxygen. It allows the whale to stay underwater longer, searching for food in the deep. When it surfaces, its heart rate speeds up again, pumping blood rapidly to refuel its massive body. Blue whales are also surprisingly fast. They can swim at speeds of 30 miles per hour when they need to. Imagine something the size of a Boeing 737 moving that quickly through water. It's a reminder that size doesn't always mean slow. These giants are also among the loudest animals on Earth, as we mentioned. Their low-frequency calls can travel across entire ocean basins. They sing to each other across thousands of miles of open water. A blue whale in the Atlantic can theoretically be heard by another in the Pacific if conditions are right. But even these massive creatures, even the largest animals ever to exist, can't reach the deepest parts of the ocean. There are places so deep, so dark, and under so much pressure that no whale can survive there. Places where the ocean becomes truly alien. And it's to these deepest depths we turn our attention now. The Mariana Trench is the deepest place in the ocean. It's a long, narrow valley in the Pacific Ocean floor, stretching for over 1,500 miles. But it's the depth that matters. At its deepest point, called Challenger Deep, the ocean floor sits nearly 7 miles below the surface. 7 miles straight down. To understand this depth, imagine Mount Everest, the tallest mountain on Earth. If you could pick it up and drop it into the Mariana Trench, the peak wouldn't even reach the surface. There would still be more than a mile of water above it. The pressure at that depth is crushing, literally. At the surface, air presses down on you at about 15 pounds per square inch. You don't notice it because you're used to it. But in the Mariana Trench, water presses down at more than 8 tons per square inch. That's like having 50 jumbo jets stacked on top of your thumb. This pressure would crush a human instantly. It would collapse your lungs, crush your bones, compress your body into nothing. Even submarines made of the strongest materials can't go that deep. Only specially designed vessels with thick titanium hulls have made the journey, and only a handful of people have ever been there. But life exists even there. Scientists have found fish, shrimp, and single-celled organisms living at the bottom of the Mariana Trench. These creatures have adapted to the pressure. Their bodies are built differently. They don't have air spaces that can collapse. Their cells can function under pressure that would destroy most life. Some of these deep-sea fish look transparent. You can see through their skin to their bones and organs. Others look like they're made of jelly. Their bodies are soft and flexible, designed to withstand the crushing force of the deep. The water down there is just above freezing. There's no light, no plants, no photosynthesis. The creatures that live there survive on marine snow, the constant rain of dead material falling from the surface miles above. Bits of dead plankton, fish waste, decomposing bodies. It all drifts down like snow, and the creatures at the bottom feed on it. This is one of the most extreme environments on Earth, more extreme than the driest desert or the coldest ice sheet. Yet life persists. Life finds a way to survive even here, in conditions that seem completely impossible. Only 4 people have ever descended to the bottom of Challenger Deep. The first was in 1960. 2 men in a bathyscaphe, a specially designed deep diving vessel. They spent 20 minutes at the bottom, looking out through a small window at an alien world. The second expedition didn't happen until 2012, when filmmaker James Cameron made a solo dive. Since then, only 2 more people have reached the bottom. Fewer people have been to the deepest part of the ocean than have walked on the moon. Think about that. We've explored space more than we've explored our own ocean. There are more footprints on the moon than on the floor of the Mariana Trench. And the deep trenches aren't the only unexplored landscapes down there. The ocean floor has entire mountain ranges we barely know about. The longest mountain range on Earth isn't the Rockies or the Andes or the Himalayas. It's underwater, and most people have never heard of it. The mid-ocean ridge system stretches for more than 40,000 miles. It wraps around the planet like the seam on a baseball. It's longer than all the land-based mountain ranges combined. And it's almost completely hidden beneath the waves. These aren't small hills. They're massive mountains, some rising over 10,000 feet from the ocean floor. If the water were removed, you'd see peaks and valleys that rival anything on land. But because they're underwater, we rarely think about them. They exist in a realm we can't easily see or visit. The mid-ocean ridges form where the Earth's crust pulls apart. Deep beneath the ocean, the planet's tectonic plates are slowly moving away from each other. As they separate, magma from the Earth's mantle rises up to fill the gap. This magma cools and hardens, creating new ocean floor. This process is happening right now. The ocean floor is constantly being created, inch by inch, year by year. It's one of the most fundamental processes on Earth, and it's happening in the deep ocean where we can't see it. At these ridges, volcanic activity is constant. Lava erupts underwater, though it looks different than land volcanoes. The intense pressure and cold water cause the lava to form strange pillow shapes as it cools. These pillow lavas stack up, building the mountains higher and higher. Some of the peaks break through the surface, forming islands. Iceland sits on top of the mid-Atlantic ridge. It's one of the few places where you can see this underwater mountain range above water. The island is literally being pulled apart as the tectonic plates move. It grows wider by about an inch each year. Other peaks stay just below the surface, creating seamounts. These underwater mountains rise thousands of feet, but never quite break through. Many of them are extinct volcanoes, mountains that stopped growing millions of years ago. Fish and other sea life cluster around seamounts because the underwater mountains create currents that bring nutrients up from the deep. The mid-ocean ridges are also home to those hydrothermal vents we talked about earlier. The same volcanic activity that builds the mountains also heats the water and creates the vents where strange life thrives. These underwater mountains shape ocean currents. Water flows around them, over them, creating patterns that affect the entire ocean. The ridges act as barriers, dividing the ocean into different regions, each with its own temperature and chemistry. Mapping these mountains has taken decades. Ships crisscross the ocean, using sonar to measure the depth and create maps of the seafloor. But there's still so much we don't know. Large sections of the ocean floor remain unmapped. We have better maps of Mars than we do of our own ocean floor. And these mountains aren't just sitting still. The ocean floor is constantly moving, constantly changing. The mountains we map today are in slightly different positions than they were a century ago. The ocean floor is alive with motion, and that motion is making the ocean grow. The ocean floor is spreading, slowly, steadily, unstoppably. At the mid-ocean ridges, new rock forms and pushes the older rock aside. This pushes the continents apart. It widens the ocean basins. It changes the face of the Earth. The Atlantic Ocean is getting wider. Right now, as you rest, the Americas are moving away from Europe and Africa. The distance between New York and London increases by about an inch every year. That's roughly the same rate your fingernails grow. It seems impossibly slow, but over millions of years, it adds up. 200 million years ago, there was no Atlantic Ocean. Not the way we know it today. All the continents were joined together in one massive landmass called Pangaea. Then the continents started pulling apart. Slowly, the rift grew wider, water rushed in, and the Atlantic Ocean was born. It's still growing, still widening. In another 100 million years, the Atlantic will be much bigger than it is today. The continents will be farther apart. The map of the world will look completely different. Meanwhile, the Pacific Ocean is shrinking. On the edges of the Pacific, tectonic plates are colliding instead of spreading. One plate slides beneath another in a process called subduction. Old ocean floor gets pushed down into the Earth's mantle, where it melts and recycles. The Pacific is slowly disappearing, consumed by its own edges. This discovery of seafloor spreading changed everything we understood about Earth. Before the 1960s, scientists didn't know the continents moved. They saw that the continents looked like they could fit together, like puzzle pieces. South America and Africa especially. Their coastlines match almost perfectly. But scientists didn't know why or how. Then they studied the ocean floor. They found that the rocks near the mid-ocean ridges were young. The rocks farther away were older, and the oldest rocks were near the continents. This pattern proved that new rock was forming at the ridges and spreading outward. It proved the ocean floor was moving. This led to the theory of plate tectonics, which explains how the Earth's surface is broken into huge plates that slowly move and shift. It explains earthquakes, volcanoes, and mountain formation. It explains why we find fossils of tropical plants in Antarctica and why there are seashells on top of mountains. The whole surface of the Earth is in motion. Always has been, always will be. The continents drift like rafts on a slow-moving sea of molten rock beneath them. Oceans open and close. Mountains rise and fall. Given enough time, everything changes. This means the ocean we see today is just one moment in a very long story. The ocean has looked different in the past. It will look different in the future. Coastlines will change. Islands will sink or rise. New seas will form where there's now dry land. The ocean isn't a permanent feature. It's a temporary arrangement of water on a planet that's constantly reshaping itself. And if we could speed up time and watch the last few 100 million years play out, we'd see oceans come and go like breathing. In, out, opening, closing. The Earth is alive with this motion. The oceans we know today are young. The Atlantic is only about 200 million years old. The Pacific is older, but still not ancient by Earth's standards. Before these oceans existed, there were others. Oceans with different names, different shapes, different shores. Oceans that have completely disappeared. The Tethys Ocean once separated the northern and southern continents. It was a vast tropical sea that stretched across what is now southern Europe, the Middle East, and southern Asia. For millions of years, it was home to countless species. Reefs grew in its warm waters. Ancient marine reptiles swam through its depths. Then the continents shifted. Africa and India moved north. The Tethys Ocean got squeezed between colliding landmasses. Slowly, over millions of years, it closed. The ocean floor buckled and rose. And what was once ocean floor became mountain ranges. The Himalayas, the highest mountains on Earth, are made from the floor of the Tethys Ocean. The rocks at the top of Mount Everest contain fossils of sea creatures, shells, coral, marine organisms that lived in warm tropical water. Now they sit at the top of the world, frozen and wind-blasted, 5 miles above sea level. This is how we know about ancient oceans. We find their remains pushed up onto land. We read the rocks like history books. Each layer tells a story. Each fossil reveals what lived there. Limestone forms from the compressed remains of tiny sea creatures. Sandstone shows where ancient beaches once existed. Shale forms from mud that settled on the ocean floor. Mountains around the world contain these clues. The Appalachians were once as tall as the Himalayas. They've been worn down by time, but their rocks still show evidence of ancient seas. The Rocky Mountains have layers of marine sediment. Even places that seem nowhere near the ocean have this hidden history. Scientists have mapped these ancient oceans by studying the rocks. They can trace where shorelines used to be. They can identify ancient coral reefs, now turned to stone and lifted high above the sea. They can tell you which areas were deep ocean and which were shallow. continental shelves. And they've learned something remarkable. Sea levels have changed dramatically throughout Earth's history, sometimes much higher than today, flooding areas that are now dry land, sometimes much lower, exposing ocean floor that's now underwater. During ice ages, when massive glaciers covered much of the northern hemisphere, the ocean was lower. The water was locked up in ice. You could walk from Asia to North America across a land bridge, where the Bering Strait is now. You could walk from England to France. The coastlines were completely different. When the ice melted, the ocean rose. Coastal areas flooded. Islands formed. The map changed again. And this cycle has happened multiple times in Earth's history. Ice Age, warm period. Ice Age, warm period. The ocean rising and falling with each shift. Right now, we're in a relatively warm period. The ocean is higher than it was 20,000 years ago, and it's still rising as the remaining ice sheets slowly melt. The ocean's history is long and complex. But one thing is clear. The ocean has always been here in some form, and it's always been essential to life. Because every living thing on Earth, including us, traces its origins back to the ocean. Life began in the ocean. This isn't theory, it's fact. The first living cells appeared in the ocean around 3.5 billion years ago. They were simple, single-celled organisms that fed on chemicals in the water. But they were alive, and from them, everything else descended. For billions of years, life existed only in the ocean. The land was barren, no plants, no animals, no life of any kind, just rock and sand and volcanic activity. But the ocean teemed with microscopic life that slowly, gradually became more complex. These early organisms changed the ocean, and they changed the entire planet. Some of them learned to use sunlight for energy. They developed photosynthesis, and as a byproduct, they released oxygen into the water and eventually into the atmosphere. Before life, Earth's atmosphere had almost no oxygen. Life created the air we breathe. Over time, ocean life became more diverse. Multicellular organisms appeared, soft-bodied creatures like jellyfish and worms, then creatures with shells and exoskeletons, then fish. Each development took millions of years. Each change built on what came before. And throughout all of this, life stayed in the ocean. The land remained empty for billions of years. Then, around 450 million years ago, plants began to colonize the shores. They adapted to survive out of water. They developed ways to support themselves without water's buoyancy. They learned to get water from the ground instead of absorbing it from all around them. Animals followed, first invertebrates, like insects and spiders, then vertebrates, fish that could breathe air and crawl on land using their fins. These became amphibians, then reptiles, then mammals and birds. Every land animal descended from creatures that crawled out of the ocean. And we carry this history in our bodies. Your blood is salty because ancient life lived in salty water. The salt concentration in your blood is similar to the salt concentration in ancient seas. Your cells still need that balance. Too much salt or too little, and your cells stop working properly. When you were developing before birth, you floated in fluid inside your mother's womb. That amniotic fluid has a similar salt balance to seawater. You began your life floating in a private ocean, just like the earliest life floated in Earth's oceans billions of years ago. Your body is mostly water, about 60%. That water needs salt to function. Your nerves use salt to transmit signals. Your muscles use salt to contract. Your kidneys work constantly to maintain the right salt balance, filtering your blood and adjusting the levels. When you sweat, you lose salt. When you cry, your tears are salty. Your body is constantly managing this ancient need, this echo of life in the ocean. Even the rhythm of your body connects to the ocean. Many biological processes follow cycles that match the moon's pull on the tides. Women's menstrual cycles average about the same length as the lunar cycle. Some people sleep better or worse depending on the moon phase. These connections might be coincidence, or they might be remnants of our deep evolutionary history. We came from the ocean, and in many ways, we've never fully left it. We carry the ocean inside us. Its salt runs through our veins. And that salt has been cycling through Earth's systems for billions of years. Your body works hard to keep salt at the right level. Not too much, not too little, just right. This balance is so important that you have entire organs dedicated to maintaining it. Your kidneys filter about 50 gallons of blood every day, adjusting salt levels constantly. The ocean does the same thing. It maintains a careful salt balance. Seawater is about 3.5% salt. That percentage stays remarkably stable across most of the ocean. The ocean has mechanisms to keep it balanced, just like your body does. When you eat salty food, your kidneys sense the increase. They work to remove the extra salt through your urine. When you don't eat enough salt, they hold on to what you have, conserving it. Your body will do almost anything to maintain that balance, because every cell depends on it. Salt allows your nerves to fire. When you think a thought, when you move a muscle, when you feel a sensation, salt ions are moving across cell membranes, creating electrical signals. Without salt, your nervous system stops working. Your heart stops beating. Your brain stops functioning. The ocean's salt serves a different purpose, but is equally vital. Salt makes seawater denser than fresh water. This density drives ocean currents. Cold, salty water sinks. Warm, less salty water rises. This creates circulation that distributes heat around the planet. Without salt, the ocean's current systems would collapse. Climate would destabilize. When you sweat heavily, your body loses salt. You can feel the effects. Weakness, dizziness, muscle cramps. Your body is telling you it needs that salt back. Athletes know this. They drink electrolyte solutions to replace what they've lost. The salt goes back into your bloodstream, back into your cells, restoring the balance. When you cry, you're releasing salt water from your body. Tears are salty for the same reason blood is salty. They're made from the same source, your body's internal ocean. And just like the ocean releases water through evaporation, your body releases water through tears, through sweat, through breath. But you take salt back in, through food, through drink. It enters your stomach, gets absorbed into your bloodstream, circulates through your body. Some of it gets used, some gets stored, some gets filtered out and removed. It's a constant flow, in and out, like waves on a shore, never stopping. The ocean receives salt in a similar way. Rivers carry dissolved minerals from rocks and soil. These minerals wash into the ocean constantly. Most of it is sodium chloride, table salt, the same salt in your blood, the same salt you sprinkle on food. This salt doesn't just arrive and stay, it cycles. Some salt gets trapped in sediments. Some gets pulled into the ocean floor through subduction. Some crystallizes in shallow lagoons and gets buried. The ocean is constantly receiving salt and removing salt, maintaining a balance that's lasted for hundreds of millions of years. Your body and the ocean both face the same challenge. Too much salt is dangerous. Too little is deadly. Both have evolved ways to maintain the perfect middle ground, and both work constantly, every second of every day, to keep that balance stable. This need for salt, this careful management of it, connects you to the ocean in a practical, physical way. The salt in your body is the same salt in the ocean, and that salt came from somewhere. The ocean's salt comes from the land. It always has. Here's how it works. Rain falls on mountains and rocks. Water is a gentle but persistent solvent. It dissolves tiny amounts of minerals from whatever it touches. Most of these minerals are salts, various compounds that include sodium, chloride, magnesium, and calcium. The amounts are small. If you tasted rainwater running off a rock, you wouldn't notice the salt. But it's there, dissolved at the molecular level. And this process happens everywhere, constantly. Every raindrop picks up microscopic amounts of minerals. These mineral-rich waters flow into streams. The streams join rivers. The rivers carry this dissolved cargo to the ocean. And once the salt reaches the ocean, it stays there. Water evaporates from the ocean surface and returns to the land as rain. But the salt doesn't evaporate. It remains dissolved in the seawater. This has been happening for billions of years. Grain by grain, molecule by molecule. Rain falls, dissolves minerals, carries them to the sea. The ocean has been collecting salt since it formed, and the concentration has built up over that immense span of time. But here's what's interesting. The ocean isn't getting much saltier. You'd think it would, with rivers constantly delivering more salt. But the salt concentration has stayed relatively stable for hundreds of millions of years. Why? Because salt leaves the ocean too. Some of it gets trapped in sediments on the ocean floor. Clay particles and organic matter bind with salt molecules, pulling them out of the water. Over time, these sediments get buried and compacted, locking the salt away. Some salt gets pulled into the Earth's crust through subduction zones where tectonic plates collide. The ocean floor, along with its salt, gets recycled into the mantle. It melts and eventually returns to the surface through volcanic activity, starting the cycle again. Some salt crystallizes in shallow lagoons and salt flats. When seawater evaporates in enclosed basins, the salt concentration increases until it can't stay dissolved anymore. It forms crystals that settle to the bottom. Over time, these deposits get buried and turn into underground salt formations, humans mine these ancient salt deposits. The salt you buy at the store might come from ancient seabeds that dried up millions of years ago. You're seasoning your food with the ocean's past. Different parts of the ocean have different salt levels. The Red Sea is saltier than average because it's in a hot, dry climate with high evaporation and limited freshwater input. The Baltic Sea is less salty because it receives a lot of river water and has limited connection to the ocean. Near the mouths of major rivers, the ocean is less salty. The Amazon River pumps so much fresh water into the Atlantic that you can find nearly fresh water 100 miles offshore. The fresh water floats on top of the denser salt water, creating a distinct layer. The ocean's saltiness affects everything in it. It influences which creatures can live where. It drives currents. It changes how sound and light travel through water. It affects the ocean's freezing point, which is why seawater doesn't freeze until it reaches about 28 degrees Fahrenheit. And all of this salt, this essential ingredient of the ocean, is constantly cycling, moving from land to sea, from sea to sediment, from sediment to rock, from rock back to the surface. An endless loop that connects the ocean to everything else on Earth. The ocean is always moving. Even when the surface looks calm, currents flow beneath. Deep currents, surface currents, currents that circle entire ocean basins, and one current that connects them all. Scientists call it the global conveyor belt. It's a system of currents that moves water around the entire planet. Warm water flows along the surface from the tropics toward the poles. There, it cools and becomes denser. It sinks deep into the ocean and flows back toward the equator along the bottom. This creates a loop that circulates through all the major oceans. The journey is slow. A drop of water might take 1,000 years to complete one full circuit. That means some of the water in the deep ocean hasn't seen sunlight in centuries. It sank near Greenland before Columbus sailed to America. It's been flowing through the dark ever since, carrying cold and nutrients, gradually making its way around the world. This circulation is crucial. It distributes heat across the planet. Warm water from the tropics carries heat northward, warming places like Europe that would otherwise be much colder. The Gulf Stream, part of this system, brings warm water from the Caribbean to the North Atlantic. This is why Britain has a relatively mild climate, despite being as far north as Canada. The ocean is heating it. The deep currents bring nutrients from the ocean floor up to shallower waters where life can use them. When deep water rises near coasts, it's called upwelling. These areas are incredibly productive. Fish gather in huge numbers because the water is rich with nutrients brought up from the depths. The ocean remembers its past through these currents. Water that sank 100 years ago carries information about what the ocean was like then. Scientists can measure the temperature, salt content, and chemical composition of deep water and learn about historical climate conditions. The ocean is an archive of its own history, written in layers of moving water. These currents are sensitive to change. They depend on temperature differences and salt concentrations. If polar ice melts too quickly, it adds fresh water to the surface near the poles. This water is less dense than salty water, so it doesn't sink as readily. The conveyor belt slows down, and if it slows too much, it disrupts the entire system. This has happened before in Earth's history. During periods of rapid ice melt, the conveyor belt has weakened or stopped temporarily. The effects are dramatic. Europe cools, weather patterns shift, ocean ecosystems change as nutrient distribution gets disrupted. Right now, the conveyor belt is flowing normally, but it's slowing slightly as polar ice melts and fresh water enters the system. Scientists monitor this carefully because the conveyor belt affects climate worldwide. Ocean currents also create gyres, large circular currents in each major ocean basin. The North Atlantic Gyre, the South Pacific Gyre, these rotate constantly, driven by wind and the Earth's rotation. They trap floating debris in their centers, which is how the ocean's garbage patches form. Plastic and other debris gets caught in these slow rotating gyres and accumulates. But currents don't just move water and debris, they move memories. They move history. They move the ocean's secrets from one part of the world to another. And some of those secrets are things we've lost to the sea. The ocean floor is a museum. It holds thousands of shipwrecks, each one a time capsule from the moment it sank. Wooden sailing ships from centuries ago, steel warships from world wars, modern cargo vessels. They all rest on the bottom, preserved by the cold, dark water. In the deep ocean, shipwrecks can last for centuries, almost unchanged. There's no oxygen to rust metal quickly, no storms to break them apart, no sunlight to decay wood. The cold temperature slows all chemical processes. A ship that sank 200 years ago might look like it went down yesterday. These wrecks tell stories. A merchant vessel from the 1600s holds cargo that reveals what people traded. Chinese porcelain, African ivory, South American silver. The goods map out ancient trade routes and economic connections we might not know about otherwise. War graves lie silent on the ocean floor. Ships sunk in battle, their crews still inside. These are treated with respect by divers and archaeologists. They're not just artifacts, they're tombs, memorials to people who died at sea. Some wrecks are shallow enough for divers to explore. Others sit so deep that only robots can reach them. The Titanic lies 2.5 miles down, too deep for humans to visit safely. Remote-operated vehicles with cameras have mapped every inch of it, but no person has stood on its deck since it sank in 1912. The ocean also hides entire cities. When sea levels rose after the last ice age, coastal settlements flooded. Ancient harbors now sit underwater. Stone structures that once stood on dry land now host coral and fish. These submerged ruins exist all around the world. Off the coast of Egypt, archaeologists have found the remains of ancient Alexandria, including parts of the famous lighthouse that was one of the 7 wonders of the ancient world. The stones lie scattered on the seafloor, covered in centuries of sediment and marine growth. In the Mediterranean, dozens of ancient cities rest underwater. Earthquakes dropped them below sea level. Rising oceans covered them. Now, divers swim through streets that haven't seen air in thousands of years. They see foundations of buildings, broken columns, pottery scattered where it fell. These underwater sites preserve things that would decay on land. Wood survives because it's buried in sediment away from oxygen. Organic materials like rope and cloth can last for centuries in the right conditions. Even papyrus scrolls have been found, readable after 2,000 years underwater. The ocean protects these treasures. There's no weather to erode them, no rain to dissolve them, no freeze and thaw cycles to break them apart. The biggest threats are currents that shift sediment and humans who disturb the sites. Archaeologists work carefully underwater, documenting everything before they touch it. Each artifact's position tells part of the story. Move something carelessly and you lose that information forever. So they photograph, measure, and map before they excavate. Every year, new wrecks are discovered. Storms shift sand and expose what's been hidden. Fishermen snag nets on unknown structures. Sonar surveys reveal shapes on the ocean floor that turn out to be ancient ships. But wrecks and ruins aren't the ocean's only secrets. There's something more fundamental it's hiding. Something about the ocean itself that we still barely understand. The vast majority of the ocean remains unexplored. We've explored less than 5% of the ocean. Think about that. After all our technology, all our curiosity, all our centuries of sailing and diving, we've only seen a tiny fraction of what's down there. We have better maps of Mars than we do of our own ocean floor. We've sent more people to space than to the deepest parts of the sea. We know more about the surface of the moon than about the creatures living in the deep ocean trenches. Every deep sea expedition discovers new species. Not occasionally. Every single time. Scientists send submersibles down to explore, and they always find life they've never seen before. Fish with transparent heads. Jellyfish the size of cars. Worms that glow in rainbow colors. Each discovery raises new questions. Scientists estimate there might be 1 million species living in the ocean that we haven't discovered yet. Maybe more. The deep sea is so vast and so difficult to explore that entire ecosystems could exist down there completely unknown to us. Some of these creatures are strange beyond imagination. There are fish that look like they shouldn't be able to exist. Their bodies seem too fragile, too weird, too specialized. But they thrive in their environment. They've evolved to fill niches we're only beginning to understand. We keep finding larger creatures too, not just microscopic organisms. Big animals. In 2021, scientists discovered a new species of whale. A whale. One of the largest animals on Earth, and we didn't know it existed until recently. If we're still discovering whales, what else is out there? The ocean is Earth's last great frontier. We talk about space exploration, about going to Mars, about finding life on other planets. But we have an alien world right here, right beneath the waves, and we barely know it. The challenges of ocean exploration are immense. The pressure crushes most equipment. The darkness is absolute. The distances are vast. Communication is difficult because radio waves don't travel well through water. It's expensive and dangerous and technically challenging in ways that space exploration isn't. But the rewards are extraordinary. Every new species we discover teaches us something about life's possibilities. Every new ecosystem shows us a different way that nature solves problems. Every new deep-sea environment changes our understanding of where and how life can exist. And there are practical reasons to explore. The ocean might hold cures for diseases. Deep-sea creatures produce unique chemicals to survive in extreme conditions. Some of these chemicals could become medicines. We've already found compounds from ocean life that fight cancer, reduce pain, and kill bacteria. The ocean also holds resources we might need. Rare minerals, energy sources, materials for technology. But we can't use these resources wisely if we don't understand the ecosystems they're part of. More than anything, the ocean deserves our attention because it's part of our home. This planet is mostly water. The ocean covers most of its surface, contains most of its life, and drives most of its climate. Understanding the ocean means understanding Earth, and understanding our connection to it changes how we see ourselves. We're not separate from the ocean. We never have been. We came from it. We depend on it. We're part of its story. And that story is far from over. So, here we are. We've drifted through the ocean's secrets together. From the surface, where tiny plants create the air we breathe, down to the deepest trenches where life exists in crushing darkness. From underwater rivers and lakes to mountains, taller than anything on land. From the songs of whales echoing across oceans to the silent flash of bioluminescent creatures in the void. The ocean breathes for us. It lights itself. It sings. It remembers. It holds our history in sunken ships and flooded cities. It connects to our bodies through the salt in our blood. It keeps most of its secrets still, waiting in unexplored depths. Picture yourself on a beach at night. The waves roll in steadily, each one unique, but part of an endless rhythm. The water stretches to the horizon and beyond, covering most of the planet. Beneath that surface, all of this is happening. Rivers flowing through water, mountains growing, creatures glowing in the dark, ancient currents carrying water that hasn't seen light in centuries. The ocean teaches us patience. It changes slowly, grain by grain, wave by wave. Mountains rise over millions of years. Salt accumulates drop by drop. Evolution works through countless generations. Nothing happens quickly in the ocean. Everything builds over time. It teaches us humility too. We've explored so little of it. We understand so little of what we've seen. We keep discovering things that surprise us, that challenge what we thought we knew. The ocean reminds us how much we still have to learn, and it teaches us wonder. No matter how much we discover, the ocean remains mysterious and beautiful. Every answer leads to new questions. Every expedition reveals new marvels. The ocean will keep amazing us for as long as we care to look. You're connected to all of this. The oxygen in your lungs came from ocean plants. The salt in your blood echoes ancient seas. The water in your body is part of the same cycle that fills the ocean and falls as rain. You're not separate from the ocean. You're part of it. As you drift towards sleep now, let these thoughts settle gently. Imagine the deep ocean, vast and calm. Imagine the slow currents, the soft, bioluminescent glow, the ancient quiet of water under pressure. Let the ocean's patience become your peace. Thank you for taking this journey with me tonight, for exploring these incredible facts together, for bringing your curiosity and openness to this quiet space. If you found calm in these ocean depths, if these facts brought you wonder and peace, I'd be grateful if you'd like and subscribe to the channel. There are more gentle journeys waiting, more science to explore in ways that bring rest instead of stress. And I'd love to have you along for them. Tomorrow we'll drift somewhere new. Another corner of our amazing world, explained simply, shared softly, perfect for letting your mind wander as your body rests. Leave a comment if you'd like. Tell me what surprised you most. Tell me which fact you'll remember. Tell me where you are and what time it is there. I love knowing where these stories travel. For now, let the ocean rock you gently. Let its ancient rhythms carry you to sleep. The waves keep rolling. The currents keep flowing. The deep stays calm and dark and peaceful. Rest well.